Hello everyone, my name is Wong Chong Hong. Today I will share our recent research, Optimal Privacy-Aware Dynamic Estimation. In our setup, a prefate process YT drives the state of the system XT. The state estimate X hat T is shared with an adversary who might use them to infer the prefate process. The objective is to minimize the estimation error and control the prefate information flow from the estimator to the adversary. In our setup, YT is the prefate Markov chain, XT is the system state controlled by YT. ZT and ZTT are the measurement and quantized measurement, respectively. This model could generally represent the following nonlinear and linear systems. The motivation of our research is the privacy leakage in HVAC systems. Occupancy of a building is often highly prefate, and sensitive information such as the mobility of the building occupants can be inferred from the occupancy. However, as shown in the left figure, the occupancy can be inferred from the CO2 measurement if the quantized CO2 level is sent to the remote controller directly. The controller could accurately infer the occupancy. The optimal privacy-aware stochastic estimation policy is the solution to the following optimization problem, where LD denotes the estimation loss. Ix hat T, YT is the mutual information between the estimation and the prefate treasury. It measures the leakage level of prefate information through the estimator. Lambda is a positive constant. The estimator has access to the quantized measurements and its past decisions, which is denoted with HT. The estimation policy is to randomly select a X hat T based on HT. We first prove that the original optimization problem is equivalent to the following luxury optimization, where we aim to find a policy collection based on X hat T and then select the estimator based on the quantized measurements. We denote the policy collection with AT. The luxury optimization problem could be transformed as the following stochastic control problem, where the temporal loss is LAT BT and the constraint is the evolution of the belief state BT. The belief state is a conditional distribution of YT-1 and zeta t given X hat T-1. The temporary loss is a function of the policy collection AT and BT. The belief state's evolution depends on the last belief, policy collection, and the decision X hat T. Therefore, the optimal estimation policy satisfies the following optimality equations, where the optimal cost-to-go function and the policy depend on the belief state. It's sufficient to summarize one part of the history, X hat T-1 with BT, for decision-making optimization. According to the optimality equation, the privacy-aware estimation is a closed-loop control problem. The stochastic controller pi star t controls the state evolution with state feedback BT and the quantized measurements zeta t. Given X hat T, a perfect adversary who might know the system dynamic, estimation policy, and the estimation result could construct its belief PYT given X hat T to infer privacy. Therefore, the estimator controls the adversary's belief about the prefate process. It's constructive to compare the optimal privacy-aware estimator with the classical minimal mean square error estimator. The MMSE estimator is computed using the expectation of xt given zeta t, as shown in the left figure. Therefore, different from the optimal privacy-aware estimator, the classical MMSE estimator is not a closed-loop control problem. The computation of the optimal estimation policy using the structural result is difficult when the time horizon is large due to two main reasons. First, The dimension of belief state increases with time, which enlarges the search space of the optimal policy. Second, the commutation of the log term becomes intractable when the horizon becomes large, as it involves summation over all possible combinations of the past and the current quantized measurements. Next, we develop a numerical algorithm for computing an optimal privacy-aware estimator. Fourth, we parameterize the policy with theta and derives the following policy gradient formulation of the objective function, where the temporary loss, it, consists of two parts, the estimation error LD and the information loss log p theta 1 over p theta 2. With this, given the temporary loss, we could update the policy with gradient descent methods. We note that the standard policy gradient theorem from the reinforcement learning literature does not directly apply to the optimization, since the objective function is nonlinear in the policy. Secondly, we approximate the information loss with variational approach. We saw the information loss could be written as GT minus FT, where GT and FT are optimal solutions of the two optimization problems. The main idea for this approximator is to separate the conditional mutual information into two KF divergence. For each one, optimize its variational representation. We could approximate GT and FT by parameterizing them with LSTMs and optimizing them via gradient descent method. Finally, we develop a numerical algorithm that first approximates the information loss and then update the estimator via policy gradient method. To verify our result, we numerically study the privacy-aware estimation of the CO2 level of a building room based on noisy CO2 measurements. We first study the trade-off between the estimation error and the privacy in two cases: optimal privacy-aware estimation and the additive noise approach. In the additive noise approach, we first use a classical minimal mean square estimator to estimate the state. Then the state estimates are perturbed using Gaussian noise with zero mean and variance to ensure privacy. In each case, we infer the occupancy based on the state estimates via maximum likelihood estimation method. According to the left figure, the total state estimation error increases as the accuracy of the occupancy estimator becomes small. This is because to increase the privacy level, we need to increase the penalty on the liquidity level of peripheral information lambda in the optimization. Also, based on the left figure, the optimal privacy-aware estimator results in a small estimation error compared with the additive noise approach. The right subfigures from A to C show trajectories of the output of the privacy-aware estimator for different values of lambda. According to this figure, the estimation error is small when lambda equals to 0, corresponding to the smallest privacy level. However, as lambda becomes large, the privacy level increases at the cost of increasing the total estimation error. The subfigure D shows the misdetection instance of the maximum likelihood occupancy estimator when lambda is equal to 0.2 and 0.4. The number of misdetection instances increases as lambda becomes large, which indicates that the occupancy estimator cannot accurately infer the occupancy as lambda increases. In conclusion, we develop an information theoretic framework for the optimal privacy-aware estimation in dynamic setting. We study the structural properties of the optimal privacy-aware estimator via dynamic programming decomposition. We also propose a policy gradient algorithm for computing the estimator based on a variational formulation of the mutual information. Our numerical results show that the privacy-aware estimation outperforms the addictive nudge approach. That's all. Thank you.